the polynomial division. So it comes from this basic relationship here. The polynomial is equal to ax times qx plus rx, where ax is a divisor, qx is a quotient, rx is a remainder. It's exactly the same as long division, which you probably looked at in, I don't know, primary school or something like that. Exactly the same as with numbers, but now it's with polynomials. So a couple of things with polynomials though. When we're dividing, the degree of the remainder must always be less than the degree of what we're dividing by. Because if the degree is greater, well, we can keep dividing. This one's a bit trivial. The quotient and the remainder are different, so they're unique. Now, it kind of makes sense, because if they were the same, you could factorise it and you wouldn't have a remainder. All right, let's have a look at one via, it's quite an old question now, 1998. So we were asked to find the quotient and the remainder, and we're dividing this particular quartic by x squared plus 1. So we set it up like we did long division with numbers all those years ago. The other thing we have to make sure of here, though, with a polynomial is we include the missing terms. So in this one there was no x cubed, but I write that down. And there was no x term either, but I write that down. So if you like, we've got a column for each of the powers. And when we divide a polynomial, we're really just dividing the leading terms. So what I'm saying here is, well, what is x to the power of 4 divided by x squared? And the answer is, of course, x squared. And then we multiply out, so x squared plus 1 times x squared, but placing the terms in the appropriate column. And then we do a subtraction. So x to the 4 cancels, 0 minus 0 is 0. Again, the difference with polynomials to numbers is we might have negatives here. We've got to be careful with that. So we have negative x squared minus another x squared gives us negative 2x squared. Then we bring down the other terms, because theoretically what we're saying is minus 0 on these other terms here to get a new polynomial. And we repeat the process, because in this case the degree of the remainder is the same as the degree of the divisor. So we keep going. X squared into minus 2x squared is minus 2. Again, let's multiply out and subtract. We get 1 minus 2, which is of course 3, but the degree of the remainder now is 0, which is less than the degree of the divisor, so that's where we stop. So our question was, find the quotient and the remainder. Well, the quotient is x squared minus 2, and the remainder is 3. It was 3. Simply divide the polynomial it asked us to do. So let's set this one up. X squared into 2x to the power of 4, 2x squared. Multiply out. And now let's do a subtraction. Minus 10 minus 6 gives us minus 4, 12 minus 2. And then bring those other two down. It's a cubic, the remainder, so we can keep going. Minus 4x when we divide by x squared. So again, multiply out. Do a subtraction. 10 minus 12, negative 2. 2 minus minus 4, 6. Now it's a quadratic, so we can keep going again. So this time negative 2. Multiply out. And now we get a remainder of minus 1, so that's where we stop. So our final division, that's what they've now asked me in part 2. If they hadn't have asked me in part 2, I probably would have written this down anyway. I mean, the question said divide. We've done that via an algorithm, but I probably would have written down the answer, which now they're asking me to write anyway. So now write it in that form of quotient times divisor plus a remainder. So we get, our polynomial can be rewritten as x squared minus 3x plus 1 times 2x squared minus 4x minus 2, and with a remainder of minus 1. Now, this comes back to graphing of polynomials again. When we had that situation of a polynomial over a polynomial, which really is a polynomial division when you think about it. So we could do that, and we'd be left with the quotient plus the remainder over the divisor. That's how we would rewrite that function. But when it's in that form, it tells us some information. Okay, first of all, if we wanted to find vertical asymptotes, well, bottom of the fraction can't equal 0. So that will tell us the vertical asymptotes. The quotient actually turns out to be the horizontal or oblique asymptote. So that's another way we could find those asymptotes. Now, what does the remainder tell us? Well, remember, you can actually cut horizontal or oblique asymptotes. It's the vertical ones you're not allowed to cut. So to find out if it does, solve the remainder is equal to 0. And that'll tell you where, if anywhere, it cuts the horizontal or oblique asymptote. So let's try this one. Y equals x plus 8x on x squared minus 9. So I've already done all the polynomial division. So we know bottom of the fraction can't equal 0. So we know there's vertical ones at plus or minus 3. So let's plot that in. There we go, so we get plus or minus 3. The oblique asymptote is y equals x. So let's plot that one in. Okay. Now, we solve the top of the fraction, so it finds where, if anywhere, it cuts. And in this case, yes, it will. It'll cut that oblique asymptote at x equals 0. And that's fine, because remember, horizontal or oblique asymptotes are telling you what's happening out at the extremities. At around 0, they're meaningless. So I'll put that x-intercept in there. And then we could work out any y-intercepts. Well, in this case, we've got it already. We know it's going to be 0. There are no other x-intercepts found. So now I can draw my curve. I know it's got to bend towards the asymptote. So over here on the left-hand side, it must do something like that. It can't be above it. Otherwise, there'd be another x-intercept. Same on the right-hand side. And in the middle, well, it's either going to do that. Could it do anything else? Well, no, it couldn't really, because imagine we reflected that, well, what looks like a cubic. It would cut the oblique asymptote again. But we've already determined it only cuts it once, that at x equals 0. So it's forced to be that particular shape. Okay, 10C, that'll do us for today.